Okay, so let's take a look at a titration. The first scenario that is that we're going to start with a strong acid and react with a strong base. How do we neutralize that? Okay, so going back to what we talked about in the previous video, up here with strong acids, we said that strong acid is going to give us 100% dissociation, but it's going to produce H3O plus. Strong base should produce hydroxide. Let's say for all intents and purposes, it's going to produce hydroxide. Okay, so what I'm saying now is that when we take a look at the water equilibrium, and I keep flipping, so I'm sorry, you're going to have H3O plus and OH minus on the product side. Usually it's just one of those two. Now we're going to have both of them. Okay. So in order for us to solve a titration problem, I'm going to present this differently than how your book is going to show it. Okay. So your book may show this, or your textbooks may show this a couple different ways. One method would be to attack this problem from the viewpoint of what we've been doing with weak acids and weak bases, and solve using that, the traditional ice table. Okay. Some textbooks tend to skip all that and try to show this from, using an equation that we're going to talk about later on called the Henderson-Hasselbalch equation. Now, what I'm going to do is show you this a little bit differently from an analytical point of view. So this is going to be like a modified 3-step table. So this way of solving the problem is not in your textbook, but I think this makes a hell of a lot more sense than going through all the other ways. So let's walk through this. All right. So for the strong acid, strong base titration, it's saying give the only chemical equilibrium of interest with its K. Well, we know that this reaction, when we take in 2 moles of water, and it's going to form an equilibrium between H3O plus and OH minus. That's the equilibrium it's talking about. Okay? And we know that there's a KW for that reaction. All right, so think of it this way. I'm going to draw a little diagram over here. On one side, and you're going to have two lines. So on the left-hand side, this is your reactant. You've got water. Okay? On the right-hand side, you've got H3O plus, and you've got OH minus, your products. Okay? So usually when we do one of these problems, we're starting with all reactant and trying to figure out where that equilibrium lies. And usually we're trying to go a little bit more towards the right. And then what I'm saying in these problems is that your H3O plus and your OH minus is going to be on the right-hand side. So what we're kind of doing this time around is a little bit different. We're going to start from the right-hand side. We're going to start with the products and try to figure out where that equilibrium is. Okay? And let's say that equilibrium lies over there. So the distance between the water and our equilibrium, that distance right there, that's the X value. That's what we solve for. So usually what we're doing is just starting with all reactant and finding the X. In this case, what we're doing with these problems is we're going from the opposite side. We're going from all products. How do we solve for X right here? And that's what we're going to do. So in order to do this kind of a problem where we're starting from the right and moving all the way to the left, we're going to have to use a modified version of the ice table. I'll show you what this means. Okay, so consider mixing 500 milliliters of 2.0 molar HCl with 500 milliliters of 2.0 molar sodium hydroxide. Give the two reactions in water. Okay, so you've got one reaction that's going to be HCl plus water is an equilibrium to give you H3O plus and Cl minus. You've got another reaction that's going like this. NaOH is dissolved in water. That gives you sodium ion and hydroxide ion. Okay, so these are what we're looking for. The H3O plus and the OH minus. All right, now this is really important. When you mix solutions, the volumes change. Don't forget about this. So what I'm going to do is rewrite the chemical equilibrium. You got 2 moles of water is in equilibrium with H3O plus and OH minus. So we're going to set this up as a table. But we're going to do everything, instead of molarity, we're going to do everything in moles. Okay. So for the first problem, or for the first half, you got the concentration of H3O plus. So at the top, you know you're mixing 500 milliliters with 2.0 molar HCl. So if we take 0.5 liters and multiply by that molarity, 2.0 mole of HCl over 1 liter, 0.5 times 2 is going to be 1.0 moles of HCl. And so that's what I'm going to write over here for the initial moles of H3O plus. Okay. For OH minus, I've got 500 milliliters times 2.0 molar NaOH. So we're going to do the same thing. And again, we're going to get 1 mole of OH minus. So think of it this way. The amount of moles of acid and the amount of moles of base are already equal to each other. So that means that the pH should be neutral. Okay. All right. So now what we're going to look at is the completion moles. So what I mean by completion moles, think of it this way. This is going to be if you've completely neutralized the acid or the base, whichever you're dealing with, whichever is the stronger. Okay. So you're completely neutralized them. So that means when you completely neutralize the acid, you should have no moles of it left, and the base should be no moles either. So you should have all water. Now, technically, we should put a 1.0 moles here, but remember, because this is aqueous equilibria, the water is in a different phase. We don't worry about it. Okay. So that's the completion moles. If now we need to figure out the completion concentration. So keep in mind the volume was 500 milliliters for both of these. So together, 500 plus 500 should give you 1,000 milliliters or 1 liter. So what we need to do is find the molarity of those. So 0 moles over 1 liter give you no molarity. And then same thing for over here for the hydroxide, 0 molarity. So now that's if we go all the way to completion. So now we need to figure out that equilibrium concentration. So this is going to be X, and that's going to be X. All right. So again, we don't touch the water because it's in a different phase, and the concentration does not change. All right. So now we solve the equilibrium calculation and give the equilibrium concentrations. So remember that Kw is going to be equal to the you know what? Let me rewrite this on top a little bit so I have a little bit more room. Kw is equal to the concentration of H3O plus times the concentration of hydroxide. Okay. Now we know that concentration of H3O plus is going to be X. That's equilibrium. Concentration of OH minus is also going to be X, and this is equal to 1.0 times 10 to the minus 14th. Okay, so we have X squared. X times X gives us X squared. That's equal to 1.0 times 10 to the minus 14th. And so if we take the square root of both sides, we get that X is going to be equal to 1.0 times 10 to the minus 7th. All right, so that means that the concentration of H3O plus is going to be 1.0 times 10 to the minus 7th molar, and the concentration of hydroxide will be 1.0 times 10 to the minus 7th molar as well. And so if we calculate the pH is going to be equal to the negative log of the concentration of hydronium ion. And we know that value, 1.0 times 10 to the minus 7th, the pH is going to be 7 even. So yes, does this make sense? Absolutely, yes, it does. Okay, because it's neutral. It's neutral because The concentration of acid equaled the concentration of base. So they completely neutralize each other. Now, what did we say about the concentrations of the conjugates of the strong acids and strong bases? Those were ignorable. All right. But that's it. So that's the 4-line method. So let's try another problem. This time we're going to change it so that way we're not tight. So that way the concentration of the acid is not equal to the base. What happens when it looks like we're at another point within the titration? So here it is. Find the equilibrium concentrations and pH for a mixture of 100 milliliters of a 0.1 molar H3O plus solution, where the initial pH, if we calculate this will be 1.0, and then 50 milliliters of a 0.100 molar hydroxide solution, the initial pH will be 13. All right, so we're going to set this up. Again, we need our equation before we do anything else because we got a strong acid and a strong base. We're going to use the autoionization of water equation. So 2 moles of water breaks down and forms an equilibrium with H3O plus and OH minus. Okay, so initially, we need to know the initial moles. So we need to do a little bit of work. I'm gonna draw an arrow up here. So if we have 0.100 liters or 100 milliliters and multiply that by 0.1 mole of H3O plus over 1 liter, 0.1 times 0.1 should give us 0.01 moles of H3O plus. Now for the next one, 50 times 0.1, so 0.05 liters times 0.1 mole of OH minus over 1 liter. 0.05 times 0.1 will give us 0.005. So we are literally halfway to the concentration of the acid. Okay, so assuming we now have to deal with completion moles. Let me write this down. All right, so what we're saying now is that which one of these is going to run out first? Well, since hydroxide ion is the one that's smaller than the acid, the hydroxide is the one that's going to run out. So what we're going to do is subtract the 0.005. Okay, so if we subtract those two, we should be left with no moles of hydroxide ion. And if we do that, subtract 0.005 moles of base from the acid, we should be left with 0.005 moles of acid left. Okay. All right, so that's assuming we go all the way to completion. Okay, so now we need to get completion molarity. Molarity, sorry, not molality. All right, so using our moles and adding the volumes up, you got 100 mils of acid, 50 mils of base, so that's going to be 0.150 liters total. Okay, we're going to take our moles, 0.005 moles, and divide it by 0.150 liters. And so that should give us a concentration of 0.033 molar. And if we take 0 divided by 0.150, that's going to give us 0 molarity. Okay, so that's the completion molarities. Now we need to get the equilibrium molarities. Okay, so what we're going to do now, since this was the completion and we're going all the way to reactant, now to get the molarity, we're starting from the left and go all the way, go into the equilibrium. So what we're going to say is that this is for H3O plus, this is going to be 0.033 plus X. And then for hydroxide ion, it's just going to be plus X because that's the one that's going to be used up. All right, so our equilibrium expression is Kw is equal to the concentration of H3O plus times the concentration of hydroxide ion. So in this case, H3O plus, the concentration of H2O plus at equilibrium should be 0.033 plus X times the concentration of hydroxide ion, which is just X. This is equal to 1.0 times 10 to the minus 14th. All right. So at this point, what we're going to do is use the assumption. So we're still going to use that assumption and say that whatever 0.033 plus X, whatever X comes out to be, it's not going to be enough to change that 0.033 molar all that much. Okay, so that expression 0.033 plus X is now going to become 0.033. Now we still have X for the hydroxide, so we got to carry that, and this is going to be equal to 1.0 times 10 to the minus 14th. So now we can simplify this a little bit. So 0.033 times X is equal to 1.0 times 10 to the minus 14th. If we solve for X, that would be 1.0 times 10 to the minus 14th divided by 0.033. And that number should come out to be 3.0 times 10 to the minus 13th. And so this is going to be your concentration of hydroxide ion. So that's how much hydroxide ion is going to be left at equilibrium. Now, if I wanted to find out the concentration of H3O plus, if we take 0.033 and add 3.0 times 10 to the minus 13th, add that X to it, that value comes out to be, that 3.0 times 10 to the minus 13th is so small, it's not going to change anything. So it's really still 0.033 molar. So that's really nice. So using that value, the pH of the solution, which is the negative log of the concentration of hydronium ion, that 0.033, if we pop that into the pH equation, that pH is 1.45. So keep in mind, we started with 1.0. Now we've just gotten to 1.45, so the pH has gone up just a little bit, almost half a unit. So one more question that we can ask is, how much of the acid was actually neutralized? So how much acid was actually neutralized? Well, keep in mind, we started with 0.01 moles. Okay, so that's how much we had before. Now, after we added the base, we only had 0.005 moles left. So 0.005 moles divided by 0.01, and then multiply that by 100%, we have 50%. So 50% of our acid was completely neutralized. All right. And then out of this, so we're asking this question. So how much of the percentage of acid was neutralized? 50%. And then how great was that change in pH? Well, remember, we started with 1 and we ended with 1.48. So it changed by about 0.8 or 0.48 of a pH unit. So almost half of a pH unit. All right. So the way that we just solved that problem is going to work for any mixture of a strong acid and a strong base. And eventually, as we kept doing a series of these calculations, starting with, adding no acid or adding no base and then adding a little bit of base at a time, eventually what we're going to do is come up with one of these. This is called a titration curve. So eventually, now the problem is that you'll be able to construct one of these. In Gen Chem 1, when we talked about titrations, what we did was solve directly for the equivalence point, where the amount of the acid is going to be equal to the amount of the base. So what does it mean by equivalent? That means the amount of the acid, the moles of the acid, is going to be equal to the moles of the base. Okay. So yeah, that is the strong acid, strong base titration.